My intent here is not to replicate anything that you could read from the textbook or glean from the lectures, but to go at your understanding of a PID loop controller from a slightly different angle, and a more intuitive angle, I think. As with anything, if you start simple, you can always add complexity later, but it's very, very hard to start off with a complicated system and then simplify it after the fact. So what is a PID controller doing? A PID controller as a whole, or really any controller, ideally is trying to replicate the behaviors of an experienced human operator. Someone who really, really knows the machine they're operating and understands its response to inputs and can maintain control. But where the PID controller has an advantage over the human operator is a human operator has to set it and forget it periodically. A human operator is not going to sit in front of a control panel tweaking the temperature on a minute-by-minute basis to be perfect. They're going to set an input to the system that will result in a certain amount of heating, a certain amount of flow, a certain amount of pressure, a certain velocity of movement, and then they're going to walk away and attend to other things. A PID loop controller doesn't walk away. It's sitting there continuously watching the process and is able to catch little perturbations in the system before they become big changes. So what are the basics of the PID? I'm going to name things a little bit differently, partly because I have an industrial background, and if you play with any of the controllers that are available off the shelf, they're not going to refer to inputs and outputs. They're going to refer to set points, control values, process values, update times. Depending on what controller by what manufacturer, you will have different names and slightly different methods of changing the coefficients, the P and the I and the D. And what I want to do is I want to pull it apart, tease it apart, to just talk about the individual components and how they interact with each other. Because when you start simple and you pull it apart and then put it together after you understand the individual parts, the whole makes so much more sense. In an industrial controller, you are going to have a few basic bits and pieces. You're going to have the input to the system, which is what you want, whether it's a flow rate or a temperature or any other, or a force or a position. What do you want as the output of the system? In the books, they're calling them inputs. In an industrial controller, it's referred to as the set point, SP. You have the process value, which is, what is it now? I want it to be some value, which is our set point. But what is it currently? That's the process value. Shorthanded PV. This is being measured from the system. That's your feedback. The output to the system is your control value. Shorthanded CV. This is what actually goes to a motor or a pump or a thermos or a furnace, a gas supply valve, whatever it is that actually takes action on the plant. And then you have the plant. The control value being changed has some effect on the plant. The plant's change is the process value. The process value is compared to the set point, and the PID algorithm inside the controller makes yet another change to the control value, which changes the plant, which changes the process value, which changes the error, the difference between the set point and the process value, and results in a new tweak to the control value. This continues until set point and process value, there's no error between them, and the control value has reached some steady state or very close to steady state value that results in the plant being what we wanted it to be. Depending on the characteristics of the plant, we're going to have a number of inputs in addition to the set point and the process value, which are your proportional value, your proportional gain, Kp, your integral, and your derivative. And one additional common thing that's going to be tweaked is the update rate. The reason this is a term is because the update rate is also very, very intimately tied with what it is you're controlling. If you're controlling a position of something that's fast moving, then you're going to need to update these values and make changes to the control value frequently. In a typical controller, the process value from the plant is being measured pretty much continuously. And that continuous change is being fed into the algorithm, resulting in what is going to be a control value change. But the control value is only allowed to change based on the update rate. To keep things fairly simple, I'm not going to talk about any specific process. And so I'm not going to talk about any specific range of values that can be set for our set point, read as our process value, or output to the plant as a control value. I'm just going to make all of them be something between plus and minus 100. With my earlier videos, I did a fairly slow walkthrough of talking about what the code was going to be and then writing out the code and then actually talking about what it did. By this time in the course, by the time you see this video, I would expect that you've already played with the Arduino enough to have some comfort programming it. So instead of doing the full drawn out description and making it in front of you, I went ahead and made this basic program, tested it, and now I'm going to show you with a little walkthrough of the program and a quick test run, followed by moving the program out of Tinkercad straight into an actual Arduino Uno in real life, and just to demonstrate that the code is the same. The program for an Arduino is just a text file, and you can literally copy and paste what you create in Tinkercad into the Arduino IDE, download it to the Arduino, and run it from the Arduino. The main difference being, because you're now, instead of simulating it in a browser Chrome window, you're actually running it on the hardware, you're going to see a huge performance boost. Because even though it's a 16 megahertz chip, which is not very fast by the standards of your desktop's multi-gigahertz, multi-core processing power, going from a software implementation of the hardware in your browser to hardware in real life has many benefits. So as far as the hardware, you do have to bring an Arduino into Tinkercad, but I don't need anything else because at this point the PID is entirely simulated, the mass is simulated, and there's no actual inputs or outputs required. You do still need to bring the Uno in so that Tinkercad knows that the Uno exists and it's going to simulate the Uno. Once you've dragged it on the screen, you can pretty much ignore it though. Here's the quick and dirty tour of what I did. So we're creating a very simple simulation of a mass being positioned in space by a basic PID loop. The mass itself has a few basic components to it. There is a mass that I'm choosing to do in kilograms because I like metric. There is a simulated mass position in space that is in meters. So right now it's at 0 meters. There is a velocity that needs to be tracked in real time and continuously. So we have a simulated mass velocity. Now, when you're initially just using proportional control, your mass is going to oscillate. And the oscillations are not going to die down at all because initially it's a frictionless environment, which for all intents and purposes, you're simulating a perpetual motion machine. So it will oscillate freely forever due to a complete lack of friction, energy losses, integral or derivative from the PID. Initially, let's just add a simple viscosity to the environment. This is, I'm calling it a mass friction. It doesn't really behave like friction. As you know, there is a dynamic friction and there is a static friction. The static friction is typically higher than the dynamic friction. There's a transition period where if you are moving if you're moving something and its frictional characteristics are such and such, there's a point where after it starts moving, it will jump to a new position and stop, then jump to a new position and stop, and it will chatter. We don't want that. So I added a very, very simple 5% per iteration loss in velocity. This is adjustable. If you set this to 1, you'll see it oscillate. If you set it to something smaller, then it increases the loss and has an increased dampening effect on whatever is happening. I decided to add gravity for obvious reasons, since we're working towards an elevator, which is operating vertically in a gravitational field of 1g. So 9.8 newtons of force per kilogram multiplied by the mass of the object. The PID coefficients. So the PID coefficients internally, we have a proportional and an integral and a derivative. Initially the integral is off and has no effect. The derivative is off, has no effect, and I've set an arbitrary gain of 1 to the proportional value. What this means, as you'll see later, is that for a 1 unit error between the input and the feedback, the output will be 1. If I was to increase to 10, then a 1 unit error on the inputs would result in a 10 unit output change. In the class and the textbook, the PID is taking inputs. There's an input, which is where you want things to be, an output, which is driving things toward you want them to be, and you have the feedback that is measuring where things are, whether it's temperature, pressure, speed, force, flow, whatever it is. If you look at an actual PID controller that you buy off the shelf for an industrial setting or a lab setting, they are going to be set point instead of input, process value instead of feedback, and control value, which is the output to your plant. Set point, process value, control value. And the error is the difference between the set point and the process value. The timing for this simulation, I'm starting off with an update rate of 1 iteration every 10th of a second, so 10 hertz. Time elapsed doesn't actually have any effect. I just added this to keep an eye on the time since the beginning of the simulation so that you can actually watch this progress as well, and possibly spit it out to a data log for offline analysis. The only thing that we need to set up in setup is serial communications, so that we can see what's happening on the serial monitor in text and on the plot graphically. At the moment, there are no actual physical inputs or outputs. There are no libraries to initialize. There's nothing. It's just the serial console to be able to communicate with the laptop. Now, for derivative, we need to be able to keep track of the last iteration's error to compare to this iteration's error to see the rate of change of the error, which in this implementation, which is not a great implementation, is looking at error between the set point and the process value as the error that everything is geared toward. That will cause problems if you do a step change in the set point, because a step change in the set point will cause a spike in the error on one iteration, which the derivative will react to pretty violently. But for the moment, we're keeping it very, very simple, and we're just measuring the error and then updating the last error on each iteration. For integral, we have to keep track of the accumulated error over time, which becomes the integral term inside the PID loop. So it has to be initialized to 0, and it needs to be a global variable so that it is accessible from any function and any other place in the program, not just inside loop. Loop is where all of the major work happens, but it's really very, very simple. I've got a lot of commentary in here surrounding a very small amount of code. On each iteration, we update the process value to be entered into the PID as an input with the simulated mass position, which will actually come from a sensor measuring position in the real world once we connect something to the Arduino. But for the moment, we're just simulating the mass position, and the mass position initially is 0. So the process value is 0. The feedback to the PID loop is 0. Once we know the process value, then we can calculate the error between the set point and the process value. So initially our set point is 0 and our process value is going to be 0. So the error is going to be 0. If we were to, and we will, set a set point of 50, a desired position of 50, and we started off with a position of 0, then set point 50 minus process value 0 equals plus 50. So the error, or the direction that the PID needs to move, is going to be a positive 50 to start. The output of the PID, the control value, the CV, is the sum of 3 different parts. There is control value proportional, control value integral, and control value derivative that are then added together to create PID CV. And this is the output to your plane. Proportional is pretty boring. Proportional has no time component. It is just simply the error between the set point and the process value multiplied by your proportional gain. Right now, our proportional gain is set to a 1. So the contribution to the output of the proportional is going to be an error times a coefficient of p. If the position error was 1 meter and we had a gain of 2, then the proportional component of the output would be 1 meter times the gain equals 2. Integral and derivative both have time components. The integral is looking at the error, And so if the error is a positive error, every iteration, that small positive error is going to be added to the integral component. I'm scaling it, so CVI is equal to CVI plus the error times the integral gain. A higher gain means a larger adjustment to the accumulated total. And because our update rate is 0.1 second, which means we're going to be executing this code 10 times per second, we want to scale this whole thing by the same 0.1 so that it matches our simulated reality. So if we had an update rate of 1, or just left this out because we were only updating the inputs and outputs of the PID once per second, and we had a 1 meter error on one iteration, and we had a coefficient of 2, that would mean that after 1 second, the integral component would be increased by 2. And then if the process value still didn't change and the error was still 1 meter, then in second 2, there would be another 2 added to the integral. And little by little, the integral will increase and increase and increase, applying an offset to the output until that offset is high enough to start moving the process value towards the set point. The derivative is a funny thing. The derivative is time related, and it is looking at the change in error, or the change in something there are various ways to do this, and very often in order to avoid weird bumps in process, like if you're running a machine that is running at 50 degrees and you want the temperature to be 75 degrees, if you suddenly change the set point from 50 to 75, then the error is going to jump in one iteration by 25 degrees. That is going to drive this code wild briefly. Just briefly. It's going to be a huge change for a small time because of that small shift. It is still enough to upset a process. So what many PID controllers will do is, rather than doing the derivative based on the error, they will do the derivative based on the change in the process value itself. I'm choosing not to do that, only because it complicates things a little bit code-wise, and I wanted to have the proportional and the integral and the derivative all being driven by the error for simplicity. But this is another one of those small problems that my code has that are fixable fairly easily, and I invite you to fix it in your own implementation. So just like with the integral, derivative is time-based, and it's looking at the difference between the error now and the error on the last iteration. And then it's just multiplying that again by the derivative coefficient, and also scaling it by whatever the update rate is. So if we had a PID that was running on a 1 second update and the error suddenly increased from one iteration to the next iteration by, let's say, 5 units on the input, and we had a coefficient for the derivative of 1, then the output would be increased on the next iteration by 5. Now, in this implementation, the derivative is being geared to the error. It's being compared to the current error minus the last error, and that term is becoming the change in the error. The change in the error is then being scaled by the coefficient d, and also scaled
by the update rate, because it's time-based, and we don't want this running 10 times faster just because we have it updating 10 times a second. And derivative is an interesting thing because it's looking at the change in error. Our application here is position. Our process value is position. Our set point is position. So it's looking at the change in position from now versus the last iteration. So the change in position over time is velocity. So derivative in this application is basically a velocity dependent break. If we run this with a gain 1 and the integral and the derivative are off, then what you see in the numbers is as the error increases toward the negative, the output increases toward the positive and catches it, oscillates a little bit with a very large process value error at steady state. Because right now the only thing keeping it from falling further is the proportional increasing with the decrease in position. Derivative, if we were to get rid of the proportional at all and go back to just a free falling mass, then you can see that the position increases over time, the velocity increases over time, and the only thing that's really limiting it is the derpy friction that I added. But if we were to add derivative, even though there's a large error, you'll see that there's no output. So it's just reacting to the force due to gravity and the braking action of our fake friction. But if we add some derivative with a 1, then as the error increases, so does the output. And what that essentially has is the effect of linearizing the position change over time, because the faster it changes, the higher the output. Eventually you reach an equilibrium point where it's falling, but it's falling at a very constant rate. It's not accelerating due to gravity anymore. If we increase the derivative further, let's say 100, then the terminal velocity is going to be considerably smaller. But the position is still going to change over time, just very linearly. It's falling, but it's falling slowly. And now we've saturated the controller, and we're causing all sorts of problems. That was quite a bit too high. So we're falling at about 7, 8, 9, 1 meter per second, and no faster, because the 9.81 Newton force from gravity is being almost balanced by the 9.3 Newton force that is being calculated based on the change in error from iteration to iteration. So if we go back to a proportional of 1, which does settle out over time, and we add derivative, which has the velocity dependent braking action. Let's say we'll go with 10. And go with 100. So I can see a tiny little bit of an overshoot, but it stabilizes very, very quickly. Now, if we increase the proportional to, say, 5, leaving the derivative in place, then the overshoot comes back. And the error is smaller. $15. The overshoot is higher. The frequency of the oscillations is higher. And the offset is now 650 millimeters, which is better and better and better. But it's not being eliminated because the derivative only acts on a changing position, and the proportional requires an error to have any action at all. So this is where we come into the integral, which is going to measure this position error over time, accumulate the position error over time, multiply it by whatever our gain is, and add it to the output. So let's go with an integral of 1, just a gain of 1. That's too slow for a video. Let's go with an integral of 10. So now, all you can really see here is that it has actually found 0. It's found 0 error. And it's finding this perfection with an equilibrium of 9.81 on the CV, which is 9.81 newtons force, positive, which is counteracting the gravitational 9.81 newtons, and everything is stable. Let's bring the proportional down so it's not so overactive. We'll just go right down to 1, which looked like this if we had a proportional of 1 and a derivative of 100 with no integral. It becomes stable fairly quickly, but we have a 10-meter error in our position. We add a little integral. And it takes a while to stabilize. Proportional of 5. And let's add some brakes with a 500 derivative. Now you can change the mass and see how that changes things. If we're currently working on a 1 kilogram mass and we become 10 kilograms all of a sudden. Now, you'll notice that the output has to saturate to put the brakes on. And on top of that, it has almost a 20-meter error in position, which is slowly being adjusted towards 0. Because at the moment, according to my simulation, the maximum force that this controller can exert on our mass is 100 newtons. For a 1 kilogram mass, that's lots. For a 10 kilogram mass that gravitationally is going to experience 98 newtons, that is barely adequate. Now, for the fun of it, let's change the set point periodically to a random value. We're going to, so I'm just going to monitor the time elapsed, and when the time elapsed is 5 seconds, I'm going to randomly update the set point to something between 0 and 100. And you'll see all those violent spikes generated by the sudden set point changes, and the fact that I'm calculating everything, including the derivative, based on the error from iteration to iteration. Okay, so as often happens when you move from a simulated system to the real-life system, there are differences, and limitations get pointed out. When I started creating the video of doing the download to the actual physical Arduino and increasing the update rate, suddenly all the numbers didn't make sense. They were changing faster or slower than expected. And coming back to the simulation to show you where I messed up a little bit, we'll point out why, if you haven't already seen it and gone, why did he do that in my first videos? So when it comes to these simulations, because this is a browser-based simulation, if we enable the printout of the time elapsed and take a look at the simulation as it is, you can see that yes, 3, 4, 5, 6, 7, 8, it approximately keeps up if we're updating 10 times per second. However, if we try and go faster than that, to update it 100 times per second in the browser, obviously that's not going to work. If we stop the simulation and we ratchet this back to 20 times a second, now we're back at approximately real time with 20 updates per second instead of 10. However, it's not good enough to do that, because when we calculate the proportional, there's no time effect. When we calculate the integral, the update rate has to be taken into account, because if we're updating it 10 times faster or 10 times slower, then we need to scale how much we're updating it by. So if we're updating it 10 times a second, then we have to update it by 1/10 of the 1 second amount. The derivative is a little bit different from the integral, because the derivative is a change per time unit, change divided by time unit, not multiplied by. That is the reason why this number in this simulation needed to be so big. If I did it right, it would have been 5, not 500. Because the derivative is looking at the difference from one iteration to another iteration, if we are looking at a smaller time slice, then we don't want to reduce it by 10. We want to increase it by 10 to get back to a change per second, change per unit time. So multiplying is wrong. I should have divided. I also made a mistake in the simulated friction. Because again, if we are simply calculating a new velocity from the last velocity based on acceleration, and then scaling that value to reduce the velocity per iteration by 5%, then it makes a huge difference whether you are iterating 1 time per second, 10 times per second, 1,000 times per second. And I don't want to be reducing the velocity by 5%, 1,000 times per second. So for this change, I need to make 2 changes in the program. One is, rather than having the simulated mass friction be a simple 95% of, we're going to change it to 5%, the friction itself. Then I can subtract the simulated friction from 100% with the simulated mass friction scaled by the update rate. And with order of operations mattering, just like in real life, that needs to have brackets. So now it doesn't matter whether we're updating 1 time per second or 1,000 times per second. If the 5% per second is scaled by an update rate of 1,000th of a second, and it's repeated 1,000 times a second, this now works. And now that everything's been corrected, the derivative is not 500, it is 5. And it won't matter whether I have an update rate of 10 times per second or 1,000 times per second. But in the simulator, in the Tinkercad simulator, we're only capable of doing about 20 times per second. Let's move this over to hardware. So if we now just select all, copy straight from Tinkercad, paste it in, select the Arduino Mega, which I'm currently using, but pretty much any Arduino will work. It's on COM11. Compile and send. And we open the serial monitor. And the Arduino can definitely run faster than this if we change the update rate to be 100 times a second. The timestamp is still keeping up well. 300-ish times per second. There will be limitations because we're currently printing out data to the serial console on every iteration. The serial communications can definitely cause lags. And if we close the serial console, but open the serial plotter instead, the behavior is now basically identical. If we had an update rate of 1 second, instead of 300 times per second, which is very difficult to see. 4 times per second, let's say. That's more visible. So we're seeing the 5-second time slices between set point changes, and we're seeing the overshoot that doesn't quite settle before the next set point change comes in. The point being, with the slight changes that take proper timing into account, we can change the update rate and not have it significantly affect the process within certain limitations. Now, let's take this simulation that's running on hardware and have the hardware run the actual physical device.